Finally, compute the steady state probabilities of semi Markov process using VIs and HIs. VIs are 1 by 4 and HIs are H1 is 1 by 2, H2 is 1 by 3, H3 is 3 by 2, H4 is 5 by 2. You substitute the values in this equation to get the steady state probabilities of semi Markov process. Now, we are moving into the second part of lecture 3, that is Markov regenerative process. Consider a stochastic process Z of t with the state space omega. Suppose that every time a certain phenomena occurs, the future of the process Z, that means Z of t, after that time becomes a probabilistic replica of the future after time 0. Such times usually random, are called regeneration times of the stochastic process Z of t, and the process Z of t is then said to be regenerative. Such a process is called a regenerative process. We consider a stochastic process wherein there exists a time points where the process satisfies the memoryless property. These time points are referred to as a regeneration points. In a Markov regenerative process, the stochastic evaluation between two successive regeneration points depends only on the state at regeneration, not on the evaluation before regeneration. Furthermore, due to the time homogeneity of the embedded Markov renewal process, the evaluation of the Markov regenerative process becomes a probabilistic replica after each regeneration because of time homogeneity, time invariant. As a consequence, all memory other than the state must be reset at the regeneration point. As a consequence, all memory other than the state, that means the future depends on the state but not the past history. AD property of inter-arrival time is making arrival instance independent and hence memoryless as the next arrival does not depend on how long the previous arrival took. Also, since between any two arrivals same pure depth process operates, hence the arrival points become regeneration time points, must be reset at a regeneration point. Now, we are going to consider the sample path of a Markov regenerative process. Through that, I am going to explain the regeneration points. Consider this sample path of a Markov regenerative process. In this stochastic process, the omega is 0, 1 and 2. Consider the simple example of a G M 1 2 queuing model. That means the arrival is a non-Poisson process. That means the inter-arrival time distributions are not an exponential distribution, whereas the service times are exponential distribution. Only one server and the capacity of the system is 2. Therefore, the state transition diagram is like this. This is a CDF of the system spending in the state 0 before moving into the state 1. The system spending in the state 1 before moving into the state 2, the CDF will be f of t. Because the capacity of the system is 2, there is a possibility the arrival can come, but the system will be in the state 2 again. Therefore, I made a self loop with the dotted arcs. Whereas, if the service is completed with the assumption of service is exponential distribution with the parameter mu, then the system can move from the state 2 to 1, 1 to 0 also the rate will be mu. So, now you see the sample path. At time 0, the system is in the state 0. The inter-arrival time is any distribution, need not be an exponential distribution. At time S1, at time instant S1, the first arrival enter into the system. Therefore, the system size is now 1. So, system move to the state 1. Now, there are two possibilities. Either the service would have been completed before the next arrival, or the next arrival occurs first before the service completion of the first arrival, first customer who is under service. So, suppose you assume that second arrival occurs first before the completion of the service completion of the first customer. Therefore, system move to the state 2 at the time point S2. Now, consider the scenario. The first customer who is under service, his service completed first before the third arrival. Therefore, the system size now it will be 1. That means earlier the system was in the state 2. Since the service is completed, the system size becomes 1 for some time. At this duration, the third customer enter into the system at the time point S3. Now, the system size is 2 again. That means initially the system state was 0. From state 0, the system moved to the state 1 because of f of t. Then one more arrival, therefore system size 2. First customer service completion, system state is 1. Then the third arrival, now the system state is 2. Then the service completion, therefore it goes to the 1. One more service completion, therefore the system goes to the state 0. Then the arrival S4. Note the time points S1, S2, S3, S4. These are all the time points in which the arrival occurs. That is nothing but the arrival epochs. Whereas this is a time point in which the service completes. This is a time point in which the service completes. This is a time point in which the service completes. We are not noting down the service completion time points, whereas we are note down the arrival time epochs, because at the time of service completion epochs, still we should know how much elapsed time of the next arrival, because inter arrivals are now it is any distribution, not an exponential distribution. If it is exponential distribution, then the memoryless property is satisfied. Therefore, the residual or the elapsed or the remaining inter-arrival time is also exponential if inter-arrival times are exponential distribution. But here therefore, at the time of service completion, we should remember the elapsed or remaining inter-arrival time. Therefore, at the service completion time epochs, the memoryless property won't be satisfied. Whereas, at the time instance S1, S2, S3, S4 and so on, these are all the time points in which the arrival occurs. At those time points, the memoryless property satisfied. Even though the system is moving into the different states in between the arrival time epochs. For instance, between the time epochs S2 to S3, the system is moved from the state 2 to 1. At the time point 2, at the time point S2, the system was in the state 2, whereas at the time point S3 also the system is in the state 2, but in between the system was in the state 1 for some time. Similarly, in between the time instance S3 and S4, the system was in the different states in between these two time epochs. And in between, even though the transition occurs at those time points, the memoryless property was not satisfied, whereas at the arrival time epochs, the memoryless properties are satisfied. Therefore, these time points are called, go back to the definition, the stochastic process where there exists a time points where the process satisfies the memoryless property. The time points are referred as a regeneration time points. So, here the S1, S2, S3, S4 are the regeneration time points. In a Markov regenerative process, the stochastic evaluation between two successive regeneration time points, that means between S2 to S3 or S3 to S4, it depends only on the state at the transition at regeneration, not on the evaluation before regeneration. That means you should remember where the system was at the time point S2 as well as where the system was in the state at the time point S3, and you don't want before the regeneration time. As a consequence, all memory other than the state must be reset at the regeneration point. Therefore, this stochastic process is called a Markov regenerative process, and I have made a sample path for a Markov regenerative process with this example, because we are going to consider the same example later. So, here S1, S2, S3 are the regeneration time points, not the time instance at which the service completion.